Our next several sections are going to be about light and optics, basically. Chapter 25 is electromagnetic waves, and then Chapter 28 is called physical optics. These are the two chapters that are going to be covered on our next test. And then we'll hop back to, I forget if it's Chapter 26 or 27, which has some more what's called geometric optics, I believe. It's just looking at optics in a different way, but it all has to do with light, what light is, how it's created, and how it behaves. So first off, a little bit of historical context. There was this guy, James Clerk Maxwell, and I came up with this handy-dandy analogy, since you guys are done with SATs. And analogies aren't even on there anymore. But so Maxwell is to electricity and magnetism what Newton was to mechanics. Maxwell was like the guy of electricity and magnetism, and he discovered a lot of stuff, and he has a set of equations that basically they're called Maxwell's equations because he came up with them, that describe how electric and magnetic fields behave. In 1864, Maxwell said that a changing electric field ought to cause a magnetic field, because they already knew that a changing magnetic field caused an electric field. So he theorized that a changing electric field would also cause a changing magnetic field. As he worked this out, he came up with the idea of electromagnetic waves. and through his math, he also discovered that electromagnetic waves would move at the speed of light. And this was this is pretty groundbreaking, because at the time there was a study, like light and optics were a thing. Newton also had a pretty important paper regarding optics. There was light and optics that were being studied, and then there was electricity and magnetism also being studied, and they were kind of separate fields at the time. But Maxwell's theory brought them together and showed that they were connected, and that light was actually electromagnetic. And his theory also indicated that electromagnetic waves wouldn't only be visible light, which was the only thing they dealt with or knew about at the time, but that there would also be other waves that we couldn't see. And these are things that we've since discovered. We call them radio waves, microwaves, infrared, UV, X-rays, gamma rays. But Maxwell was the first guy to theorize that those kinds of waves would exist, and that they would be like visible light. We just couldn't see them. Another famous name around this time that you've heard of, but you may not have known it was a name, was this guy named Hertz. That's where the unit for frequency comes from, was his name. He was the first one to create and observe electromagnetic waves. I'm going to abbreviate electromagnetic as EM, because electromagnetic is a long word to write. And this guy named Marconi, who I'd never heard of before, but this guy named Marconi was the first to come up with the idea of using electromagnetic waves for communication. And in 1896, he was over in Newfoundland, and he successfully received a signal from England. And this, of course, is the basis for essentially all of our modern communication. Was the basis for the radio and television, and ultimately, everything we have that communicates over long distances. So these are some of the big names in terms of electromagnetic waves. But if you're going to remember one, remember Maxwell, because he is the guy of E&M. All right, so let's talk about how electromagnetic waves are created. And they can be created in multiple ways, and like they're created by our light bulbs, they're created by the sun, and many other sources. But the first way that they were created artificially was that there was this very long there's this long antenna and they're hooked up to a source of alternating current, which you diagram with a circle with this little squiggly through it. Hooked up to a source of alternating current. So at some point while this current is flowing, things would align so that there were positives up here and negatives down here, but then which generates a downward electric field. Now this is an alternating current, so this is kind of an extreme arrangement, and then a little bit later on maybe there was a few less negatives up down here, a few less positives over here, so there's still an electric field, but it's smaller. And then at a later time the charges would all be equaled out, so there might be no electric field, and then at a later time they might be oriented the opposite direction, so there's some electric field here, and then it would get bigger, and then it comes back down because of this alternating current. And so what's happening is that we have this electric field being generated that falls under the envelope of a sine wave. and this is the electric field that corresponds to an electromagnetic wave. Okay, that's kind of one way of generating is with this antenna that's hooked up to an alternating current. It's not really a circuit, it's just a long wire, so there's some space for charge to move around, but because the current's alternating, then charge will collect on one side and then just kind of move back to the other side and, oscillate back and forth like that. Now it turns out there's also an electromagnetic wave. It's called electromagnetic. There's an electric field. There's also a magnetic field. And I'm going to attempt to draw this, which is a bold proposition. There's a good diagram in your book on page 875 that I'm going to attempt to reproduce, but it's sort of a 3D drawing, and that's hard for me to do, so bear with me. All right, here goes. Now here we have a set of axes in 3D space. So let's say our electric field is oscillating in the z direction. Okay, the envelope for the electric field would look something like this. And again, bear with me. I am on 2D paper attempting to draw something 3D, and I'm not the best artist to begin with. So this would be what the electric field envelope kind of looks like. At this point, the electric field is this. At this point, it's bigger, and it's smaller again, and so on and so forth. And there's a magnetic field that goes along with this that is perpendicular to the electric field. That doesn't really look like it's going in the z direction. Oh well. There's a magnetic field that goes along with this that's perpendicular to that electric field, and it oscillates in sync with it, but not in the same plane. So this is our magnetic field. So the magnetic field is maximum at the same points where the electric field is maximum, but pretend those look perpendicular. So that if let's say that this the electric field is oscillating in the z direction, then the magnetic field has to be oscillating perpendicular to it. So it could be in the y direction or it could be in the x direction. In the case that I've drawn it, we'll say it's in the y direction. And then the wave is also moving. It is propagating is the technical term. It's propagating in space. And the direction of propagation is given by the right-hand rule. If we use our right-hand rule with the electric field and the magnetic field, then we can determine the direction of propagation. It's not, the velocity isn't equal to E cross B, but that gives us the direction. So if our electric field is in the z direction and our B field is in the y direction, so here our electric field is in the positive z direction and our B field is in this way. I guess that's the positive y? Yeah, that would be positive y. So I put my hand in the z direction, curl my fingers in the y direction, and my thumb points over in the x direction. So in this case, the velocity is in the x direction. And the direction of that velocity is determined by using the right-hand rule. So you point your hand in the direction of the E field, curl toward the B field, and that'll give you the direction that the wave is moving. Okay. So at this point in time, there's a maximum E field at this x value. If you go a little bit later, then this is going to move, and so then maybe this point on the wave will be at that point on the x-axis, and there will be zero E field and B field at the same time. But again, that direction is just determined by using the right-hand rule. Electromagnetic waves can also be detected by antennas. They can be produced by an antenna with an alternating current. They can also be detected by an antenna, because if you have a long antenna and an electromagnetic wave hits it, then there's an E field acting at the point of that antenna, and so charge can flow up and down the antenna, and the antenna can interpret that flowing charge as whatever it's programmed to interpret it as. And so that's how radio communication works, more or less. You have an electromagnetic wave being generated at one point by an antenna, and then that wave propagates, and when it hits another antenna, then it causes the charge in that antenna to move. And that's the basic principle for our communications and for listening to radio stations and things like that. More generally, we've got this antenna that can generate electromagnetic waves. More generally, any accelerated charge, an accelerated charge generates isn't the right word, radiates electromagnetic waves. So, and that's the principle behind all creation of electromagnetic waves. In the sun, there are charges accelerating around. That's why the sun produces light. There's a fission reaction going on that gives the electrons, a bunch of energy, and they get accelerated. And so that's where that radiation comes from. And these waves are radiated perpendicular to the acceleration, meaning that if you've got a detector, straight above this antenna, it wouldn't see anything because there's nothing being radiated in that direction. Whereas, if you've got another antenna over here, then the waves being radiated in that direction, we'd see it. The charges are accelerating up and down on this wire, and so if you're, as long as you're in the same horizontal plane, then you would be able to detect the wave being radiated. But if it's up here, then you won't be able to detect anything.